Welcome to this edition of Lakeside Physics. In this video, we will introduce you to the topic of momentum and the idea of conservation of momentum. So first, what is momentum? Well, momentum is the amount of inertia an object has in motion. So while inertia just dealt with mass and whether an object was moving or at rest, it had the same inertia, momentum brings in the fact that something that is moving seems to be different than something that is at rest. So momentum is equal to the mass times the velocity. We will use a P for momentum, an M for mass, and V for velocity. Momentum is a vector. The direction matters. So unlike energy, when we were talking about kinetic energy, which was a scalar, the direction didn't matter. With momentum, it will matter. The units of it are kilograms meters per second, and this is not defined as a new unit. We just write it as kilograms meters per second. So let's now consider conservation of momentum. Momentum is useful because it is a conserved quantity. The total momentum of a system will remain constant if the sum of the external forces acting on the system is zero. Another way to say this is that the sum of the initial momentum equals the sum of the final momentum. So what do we mean by a system? A system is basically a group of one or more objects. External forces are forces acting from outside the system. So if we consider for a moment a single object, all forces acting on that object will be external. If the sum of those forces is zero, it will maintain a constant momentum. For a system with two objects, an example of internal forces would be object A applies a force to object B applies an equal but opposite force to object A. Those two forces act on objects within the system, so we consider them to be internal. So they would not change the total momentum of the system. They might change the individual momentum of each object, but not the total momentum of the system. This concept of conservation of momentum turns out to be very useful for collisions and explosions. So let's consider an example where we have what you might call an explosion. We have two carts with a spring that is compressed and attached to the cart on the left. Initially, the spring stores elastic potential energy. When I release the spring, that stored potential energy will convert to kinetic energy of the two carts. Now let's consider this in terms of momentum. Initially, the momentum of the system is zero. After the collision, or explosion in this case, the momentum is also zero. We have one cart move to the right and one cart move to the left. The carts have equal masses, and it appears that the velocities are pretty close to equal. So that total momentum is still zero. Let's take a look at the forces to see if we can understand this internal versus external. So initially, before this explosion, the forces acting on the carts are just the normal force and weight. These would be considered external to the system, but they sum to zero. During the collision, there's still the normal force and weight, external but summing to zero, so that's okay. Then there's an additional force that causes the carts to move off. Now, cart A applies a force to cart B, and cart B applies a force to cart A. These are equal but opposite Newton law pair that are still considered to be internal to the system. Therefore, the sum of the external forces acting on the system is still zero, and we can consider momentum to be conserved. Alright, so let's consider how collisions affect the energy of a system. During a real-world collision or explosion, energy is not conserved. Explosions add energy, while collisions lose energy due to heat loss. Two pieces of vocabulary to consider. Inelastic collisions are collisions where the objects stick together. This type of collision results in the greatest loss of energy. Elastic collisions are collisions where the objects separate and energy is conserved. This is an ideal collision, meaning that you rarely see it actually in the real world. This is the only type of collision that conserves energy. Note that even if two objects separate, it is most likely that energy was not conserved. Whether or not energy is conserved during a collision, momentum often is, and that is why momentum ends up being a useful concept to use. So let's consider steps to solving a momentum problem. First, we want to pick a before and after. In general, this is going to be immediately before the collision and immediately after the collision, so that the friction and air resistance don't significantly change the momentum. We'll write down and consider that the net momentum initial needs to be equal to the net momentum final. If you have a collision that's in more than one direction, you can set this up into thinking about the x direction and the y direction separately. Write one momentum term per object for before and one momentum term per object for after the collision or explosion or whatever it is. Be careful with signs. Momentum is a vector. Solve. If you get stuck, consider using a new concept. Note that if the sum of the external forces does not equal 0, you will need to consider the impulses caused by these forces. Note, we'll talk about this more later, so don't worry about the impulses. For the time being, we will just be concerned with situations in which the sum of the external forces is 0, and we can consider the momentum to be conserved. So let's start with an example. A 65 kilogram person is at rest in the middle of an ice rink. The person is holding a 1.8 kilogram medicine ball. The person throws the ball at 7.0 meters per second forwards. What is the speed of the person immediately after the ball is released? Well, for this, our before is going to be when the person is just holding the ball. The after will be right after the person has released the ball. We will say that our initial momentum equals our final momentum. And for this, we will have that the momentum of the person initially plus the momentum of the ball initially will equal the momentum of the person final plus the momentum of the ball final. Now, in this particular case, note that neither the person nor the ball were actually moving initially, so both of those terms are just 0. And then we can simplify our wording by just using a P subscript for the person and a B subscript for the ball. So we can plug in the information we know and solve, and we get that the final velocity of the person is negative 0.9 meters per second. Notice that as they push and throw the ball forward, the ball applies a force to them backwards, causing them to move in the opposite direction. The total momentum of that system, the system being the ball plus the person, remains constant. Now let's consider another example. We have a 0.35 kilogram bullet traveling at 485 meters per second and it hits a 4.0 kilogram block of wood. The block of wood is initially at rest. The bullet strikes the block and emerges from the other side with a speed of 245 meters per second. Assume the block loses no mass as the bullet passes through it. What is the speed of the block immediately after the bullet has emerged from the block? Let's first start by drawing a picture. Often it will be useful to draw a before and after picture. So before, we have this bullet coming in at 485 meters per second to the block, which is at rest, and afterwards we see the bullet has gone through the block and it's moving at 245 meters per second. So again, initial momentum has to equal the final momentum. We have the momentum of the bullet initial plus the momentum of the block initial equals the momentum of the bullet final plus the momentum of the block final. Now in this case, one term is 0, which is the initial momentum of the block, so we can put in a 0 there. And then we have a mass times velocity term for each of these individual terms. We can then plug in the information we know and solve, and we get that the final velocity of the block is 2.1 meters per second. If the bullet had emerged with a speed of less than 245 meters per second, would the block have been going faster or slower than your answer to part A? Well, if the bullet was going slower after the collision, then the block must have been going faster in order to keep that total momentum constant. Did the collision conserve energy? Well, it seems doubtful. Does not look like in any way that it would be an elastic collision. This bullet went through the block. Seems like energy was probably lost. Let's prove it. So we can find the initial kinetic energy of the bullet plus the block is 3,700 joules. And we can find the final kinetic energy of the bullet plus the final kinetic energy of the block, and we get that to be 1,100 joules. So clearly we have a difference that we've lost 2,600 joules of energy from this collision. Let's do a third example. Now we've got the two objects that are moving in different directions. So we have an 1,800 kilogram truck is driving due north at a speed of 12 meters per second, and a 950 kilogram car is traveling due east at 14 meters per second. They arrive at the same intersection and both fail to yield, resulting in an inelastic collision. Recall, an inelastic collision is when the two objects stick together. This would be an extreme collision where they become entangled with one another, which is not an uncommon thing to happen within an accident. So let's first consider what direction will the tangled wreckage travel immediately after the collision. Well, they're now going to be combined. If we think about it, there was some momentum to the east and some momentum north. So the combination has to be something that is sort of northeast. So A and E don't make any sense because of the fact that with A, it's only north, with E, it's only east. So I think we can cut out A and E. Now, if we consider if it should be B, C, or D, we can consider, is there more momentum to the north or is there more momentum to the east? Well, given that the mass of our car moving to the north is almost twice as big as our car moving to the east, it seems like a reasonable conclusion then that, and we could find this by just multiplying the two together, that there is more momentum north than east, which leaves us with vector B. So now let's consider find the velocity of the wreckage immediately after the collision. So again, we want to think about breaking this up into two dimensions. We're going to have our momentum in the x direction and our momentum in the y direction. Let's first start in the x direction. So we're going to have our momentum of the car, x initial plus the momentum of the truck x initial has to be the momentum of the car plus truck final. So if we look at this total momentum, the car is moving in the x direction, but the truck is not, so we have a zero term there, and that has to equal the total mass of the car plus the truck times the final velocity in the x direction. So if we plug in our values and solve, we end up getting that the final velocity of the cars together in the x direction is 4.8 meters per second. Now let's consider the y direction. So in our y direction, this time our car has no momentum in the y direction, but our truck has momentum in the y direction. And that has to be equal to the total momentum of the car plus the truck after the collision. So if we plug in our values again, we end up with the final velocity in the y direction needing to be 7.9 meters per second. So we can now consider putting this all together. We have a velocity triangle, which we have 4.8 meters per second to the east and 7.9 meters per second north. So our final velocity will be the yellow vector. We can find the magnitude by just using Pythagorean's theorem, and we get 9.2 meters per second. And we can find the tangent using inverse tangent of 7.9 over 4.8. We get that the angle is 58 degrees. That's it for this video. Let us know if you have any questions. Thanks.